So here I have I think this is a figure from Forsyth and Pons, maybe it's from Sliski, I hope their lawyers aren't watching, it's somebody. And basically it talks about how you can transform an image. And so on the bottom left-hand corner you have a square, and you can see you could just translate it. They call it Euclidean, but that's just a rigid transformation where you have the rotation translation. You have similarity, affine, and projective. And we're going to talk about each of those in terms of the mathematics. So let's take the simplest example. So the simplest example here is translation. So we have an x, and by the way, in this cool little figure, sort of the original x and y is the green box. And we take our x and we just add some translation vector to it. And we saw that it was an easy way to describe this using homogeneous coordinates, where we just do x, y, and 1. We add a 1 to the end, and then we can just have a transformation matrix here, which is just made up of an identity plus the translation vector that we had from over here. And to keep the whole thing in homogeneous coordinates, we would just say, we would make instead of a 2 by 3, we would make this a 3 by 3, so that 0 vector now is on the bottom row, and what we would do is we get from one homogeneous vector to another. Okay? So that would be translation. By the way, because these are now just matrix multiplications, we could chain these transformations. So we also have talked about projective transformations. And remember for 3D we said that we used 4-length vectors and we had 4 by 4. Well, for 2D images it's just a 3 by 3 matrix applied to a homogeneous coordinates. So here I've written this as I have an original vector x, y, w, w being the homogeneous coordinate. I apply my 3 by 3, I get a new x prime, y prime, w prime, and of course to go to the non-homogeneous I have to divide through by the w prime later. So using this sort of general framework we can look at all of the transformations. So let's go back to translation. So translation in this framework is just the identity matrix up here, the translation there, the 0, 0, 1 there, and we go from x, y, 1 to x prime, y prime 1. In fact, we didn't have to do any division because we maintained that 1. And that's drawn with this cool little picture here where we just take this square and we can just translate it around. Nothing changes orientation, size. And translation preserves the lengths and areas of objects, so as I move them around, the angles stay the same, even the orientation stays the same, and because this is a projective transform, lines remain lines. And lines remaining lines is going to be key to everything we do for at least 5 lessons. Well, 4 or 5 lessons. All right, so that's translation. A rigid body transformation can be represented this way as well. It's called Euclidean or rigid body. And now, instead of having just a pure identity matrix, we have this rotation matrix. So we can rotate in the plane, and we can translate. So we have 3 degrees of freedom here. And again, we've maintained a rigid body, so lengths and areas are all preserved, angles are preserved, lines are preserved, but of course the location and the orientation can change. Another one which people don't think of quite as much is what's called a similarity transform. In a similarity transform, we have translation here, the rotation by the thetas, and you'll notice everything is scaled by A. Okay, so that's an expansion, that's a scale. So there's translation, rotation, and scale. So how many degrees of freedom of that? 4, right? 2 for translation, a rotation, and a scale. Now, one that we use actually a modest amount in computer vision is what's referred to as an affine transform. Okay, and an affine transform, you'll see that we have 6 degrees of freedom here, and I've just written them as a linear transformation, A, B, C, D, E, F. Okay, and again we go from x, y, 1 to x prime, y prime 1. And what an affine transformation can do is essentially map, and we'll look at this later, any 3 points to any other 3 points. All right, and what you do is you're essentially now being able to translate, rotate, scale, and skew the image. And there's skew in both directions, so there's 6 degrees of freedom. You still maintain parallel lines, so the edges of this square become the edges of a parallelogram. Okay, and ratios of areas remain the same. So if I had one area here that was half the size of the area to the left, then its transformation would be half the size over here. But the area itself can change right through scaling. All right, and again, lines are mapped to lines. Notice that we don't have to do the division still. Remember, these are homogeneous coordinates. So here I wrote it instead of with W, but with S's, right? So it's full homogeneous coordinate system, which will go from the homogeneous xy1 through a linear operation to a scaled version of the new x prime y prime, all right? So the full transformation is referred to as a general projective transformation or a homography. And a homography still maps lines to lines, because remember we talked about perspective transforms always maintain lines. And things that are inside of each other stay inside of each other. But this is what's typically sometimes referred to as perspective transform, right? So the idea is if I had a plane and I was very close to you and I tilted it this way, and we'll do more of this later, the edge that's near you will seem longer than the edge that's farther away from you. And we'll prove later that the transformation of a plane can be represented this way. Now, of course, because this is a homogeneous transform, I can scale everything by a constant and it has no impact. So I can make this last degree of freedom be a 1, right? And I'll get a slightly different W, but it doesn't matter because I'm going to divide everything through by W anyway. So that 8 degrees of freedom, that's the full homography. It's referred to as the homography.